So for our last challenge sample, we've prepared a surfactant solution made of a very common surfactant, sodium dodecyl sulfate, or SDS, in water. The concentration of the SDS is 20 millimolar. Now its critical micelle concentration, the concentration in solution at which it begins to form surfactant micelles, is around 8.2 millimolar. So we're just above the critical micelle concentration for this surfactant. The free surfactant is very small in size. It has a molecular weight of around 290 Dalton, which corresponds to 0.2 nanometers in radius. The micelles are larger in size. They have a radius of around 1.9 nanometers. Still very difficult to size by dynamic light scattering, right near the limit, but still detectable in our instrument. And they're highly negatively charged particles, so they have a very negative mobility and a very negative zeta potential. They're very stable. So we're going to see if we can size these with the Delsimax Pro. We're going to take advantage of one of the tools under calculations known as the optimization calculator. Now, this optimization calculator, we enter in the molecular weight of our particle, which in this case for a surfactant is 0.3 kilodalton. We enter in the concentration. Now it's 5.76 mgs per mil, or milligrams per mil. That's what corresponds to the 20 millimolar concentration. So we'll enter in 5.76 mgs per mil. And it says that if we have an acquisition time of 8 seconds, we need 10 acquisitions total. So we can get both the size of these surfactant molecules, their micelle, and their zeta potential in 80 seconds is what this calculator is telling me. So I'm going to go with parameters. I'm going to enter in those parameters. 8 seconds of acquisition, 10 acquisitions. I'm going to run zeta potential for the full 80 seconds to get an accurate sizing, or accurate stability. And then we just press go on the start button. Now we can monitor this reaction and measurement in real time. We can first look at the dynamic light scattering signal. Now this is with cumulant analysis where it's only picking out one peak. It's giving us a much larger than expected size. However, when we go in the regularization graph, it's going to pick out multiple peaks, and that's where we're actually going to begin to see the small surfactant micelles. So you see here we have a number of peaks because this measurement is still being done in real time. But you see our smallest peak is right at 1.8 nanometers, exactly where we expect the micelle peak to be. We have larger species, which is actually a conglomeration of the surfactant micelles of the SDS. So let's go to the measurement table. We see a mobility of minus 41 millivolts for zeta potential and mobility of minus 2.9. This is in line with what we expect. We expect a highly negative zeta potential for SDS micelles, somewhere between minus 40 and minus 45 millivolts. And the radius by cumulant analysis says the average radius is 71.7 nanometers. But we know that there's multiple species in there. And when we go at regularization, we see 1.8 nanometers, 25.3 nanometers, and then larger species. What we don't see is the very small surfactant molecules that are roughly 0.2 to 0.3 nanometers in radius. And this is because our instrument's not looking for them. On the instrument setting, we have a range that says the lowest peak it's going to look for is 0.5 nanometers in radius. When we adjust this down to 0 nanometers in radius, the calculation will be redone, and you see that there's a number of particles in solution that are 0.1 nanometers in radius, which is right around where we're expecting the radius of the free surfactant to be. And we still have a large amount that's at 1.8 nanometers. So this is the surfactant micelle. When we look at it by mass, so this is by intensity of signal. When we change this to just intensity by mass, we see predominantly free surfactant, and all the larger peaks disappear. Now if we go back and fix into the fixed parameters, and we just concern ourselves with the micelles, which is what a typical researcher would concern themselves with, we see that the majority of the peaks above 0.5 nanometers in size are the free micelle. They make up 98% of the mass of the sample. So we're able to size sodium dodecyl sulfate micelles with high accuracy at low concentrations just above its critical micelle concentration. When we look at the mobility graph, we see a very tight graph where all the points line up very well. And out of the 31 detectors, it looks like all but 4 detectors agree that the mobility is highly negative. The first detector that does not agree is the first detector, the second detector, the fourth detector, and the third detector. So those first 4 detectors are actually measuring a lower mobility. And this is due to the larger particles in solution. Those first 4 detectors measure small angles. The larger clumps that we picked up that were about 1 micron in size only scatter light at small angles of detectors. So their scattered light is only picked up by the first few detectors. The detectors with larger angles, detectors 5 through 31 that have angles ranging from 5 degrees up to 14 degrees, pick up the light scattered by the smaller micelles. So these are the ones that are accurately measuring the mobility of the micelles, whereas the first 4 detectors were measuring the mobility of the larger aggregate molecules that we're not as concerned about. The software allows us to select and deselect data points that are bad due to dust events or aggregation. So in this case, we deselect the data points that don't correspond to what we are aiming to measure. By eliminating these detectors from the measurement, we can go in here, we can mark them on the data table. By marking them, we're going to tell the software, do not count these data points in the measurement. You see, they had zeta potential between -29 to -7, whereas the rest of the detectors have zeta potential above -39. So now when we go to the data, we see that the zeta potential is -47 millivolts. It's even more negative, and that's because we've eliminated the first few detectors that are erroneous, or not erroneous so much as looking at larger aggregated molecules that we don't concern ourselves with in this measurement. So at this point, we've accurately sized and measured the mobility of very small surfactant molecules. So this is as challenge of a challenge sample can get. We are pushing the limits of light scattering as a technology with the DelsaMax Pro instrument.